This is the first lesson in Cycle 3 of the Grade 12 Advanced Functions course. And again, we're going to cycle back and go through different things to do with the various polynomials that we've learned about. Sorry, not polynomials. We are going to start with polynomials, but what I meant to say was functions. So we're going to look in this cycle at polynomials and rational and exponential and logarithmic and trigonometric functions. But the focus of this cycle is going to be using algebra to solve problems with them. So, yes, we're starting with polynomials for this one. And we're going to start with looking at factored form of polynomials. So, you know factored form of a quadratic. Let's see, if I was to do factored form of a quadratic, it would look about like this, and we wouldn't have all this other stuff here on the end, right? That is a quadratic factored form formula. But if we add other factors, then we can have factored form of a cubic or a quartic, and so on. Now we need to talk about the nature of zeros or x-intercepts, and I've filled this in ahead of time a little bit just to save some writing, but when we talk about single roots, another way we could describe that is order 1. Let's just highlight these things so that I can make them clearly be together. So single roots are order 1. What we mean by that is there's no exponent on a bracket. So in this case here, where we've got y equals x minus 1 times x plus 2, there's no exponents written outside these brackets like there are in these cases, which we'll get to in a minute. We'll call that order 1. There's assumed to be exponent 1 on each of those. I'm sure you remember this, but the zeros for a factored form of a quadratic are I just get this number, take the opposite sign of it, take this number, take the opposite sign of it, that gives me my zeros. I've got this in Desmos so that we can take a look at it and confirm that. But there you can see it. There's the zeros, -2, and at +1. But we can have other exponents on the brackets besides just 1. So we could have, for example, the exponent 2. So I took the same factors, x minus 1 and x plus 2, but I put a squared on each one of them. And I've already drawn the sketch, but let's see it in Desmos first. So I'll turn this one off, turn this one on, and there's the shape. Take a look at what happens. The zeros are still -2 and -1. But what's different, let's put this one back, the quadratic there. On the quadratic, the graph, let's read the graph from left to right. So it's coming down, 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 hits the x-axis, and passes right on through. Then it keeps going, hits the vertex, turns around, goes back up, hits the x-axis again, and passes right on through. Let's compare that to this one. From left to right, we go down, down, down until we hit the x-axis, and it turns around at that point and then goes back up until it hits the local maximum, goes back down again, hits that x-axis again, and turns back at that point. So the fact that it's an exponent 2 is causing it to turn back. Just touch it and turn away. And we're going to see in this course that any even exponent on a factor, like we have 2 in this case, is going to make that happen. And so then I've drawn the sketch over here. And then we have if we have a triple root, in other words, exponent 3 on a bracket, like the single root, the order 1, it's going to pass through. So anything with an odd exponent is going to pass right through. But notice how it's not a straight passing right through. Again, let's go see it better here. It's passing right through, still has the same zeros, but it's not going straight through. It does what I'm going to describe as a little jog to the left or to the right. So it still comes down, hits the x-axis, keeps going through, but it's like it slows down almost when it hits that x-axis if it's got degree 3 roots. And so again, anything with an odd exponent on a factor is going to go right through. Anything with an even exponent is just going to touch that x-axis at that point and turn back. And then of course we can have a combination of them, which I didn't draw out, but I did put here in Desmos. So what happens if I have x minus 1 squared and x plus 2 cubed? Well, there's no problem. I can combine them. I can mix and match them. And so now I've got negative 2, and 1 is my x-intercept still. But at negative 2, where it's an odd root, degree 3, or order 3, it passes right through. Where it's positive 1, where it's order 2 factor, it touches it and turns back. Overall, the degree of the function is if I add up all the exponents. So if I add that 2 and 3 in that last function that we can currently see, overall the degree of the polynomial is degree 5. And then if we think about that, that fits, you know, if we take a step back and look at the whole polynomial, it does look like degree 5. It's passing from quadrant 3 up to quadrant 1, and that's what we would expect it to do. So with that information, we can actually just draw sketches, and this unit, this cycle is not about using Desmos. Of course, you can still use Desmos to check your work, but the stuff we're going to do is not starting with the graphs. It's going to be sketching graphs by hand or doing other things. So don't automatically go to Desmos from here on out. So let's sketch this graph. So what can we do? Well, I need to know a couple of things. I need to know the overall degree of the polynomial, and if I add this order 3 root with this order 1 root, try to do that green, with this order 1 root, that's going to be a 1. Overall, the degree is 4. So we're going to add those individual exponents if it's in factored form. The leading coefficient is negative 1. That means it's going to be a degree 4 that opens downward. Sorry, it's not negative 1. It's negative, but this one's a little bit different because of the fact that there is a 2 inside these brackets here. If there is nothing in front of the x's inside the brackets, I could just take a as what's out front, but this one's got that 2 in there. So if I cube that 2 to the exponent 3, I could then take it out, and the leading coefficient is actually negative 8. Don't worry about that for now. I mean, it's important that it's negative. We'll talk more about why it's 8 if you didn't quite get that. End behavior. Well, if it's an even degree with a negative leading coefficient, then the end behavior is going to be like a parabola opening down, which means as x goes out to the left, negative infinity, y is going to go down towards negative infinity. As x goes out to the right, positive infinity, then y is going to still go down towards negative infinity because it's a parabola opening down. That's what we're looking at. The x-intercepts, we can clearly see that one of the x-intercepts should be 3 from that second bracket, but the other one has got that 2x plus 1 inside it. And you can either do it in your head, or you can just remember that if I set this bracket to 0, that's going to give me my x-intercept, so I could solve that, and x is going to be negative 0.5 is my other x-intercept. And the y-intercept, remember we let x equal 0. If I put x equals 0 into this equation, what I get is y equals negative, and then the 2x disappears. I'm just left with 1 cubed, and x minus 3. Again, the x disappears. I just have minus 3. So 1 cubed is 1, and times the negative sign gives negative 1, times negative 3 gives positive 3 overall. So that's my y-intercept. So with all that, I can do a half-decent sketch of my shape of my function. So it's got a y-intercept at 3, it's got an x-intercept at negative 0.5. It's got another one at positive 3. We also know that at negative point, it's going to be opening, coming up this way and, going down this way on each end. But before I get to that, we also know that this is a degree 3 root, so it's going to have that little jog thing going on there. So it's going to come up, it's going to do a little something where it sort of does a little jog to the right there. It's going to go through here. My guess is it's going to keep going a bit higher. I don't know how much higher, but somewhat higher, because otherwise shouldn't do anything else other than turn around at some point and then come back down and pass right through this order 1 root. So that may not be exactly right, but I think it's a decent sketch. The main thing that I would not be sure about is what the maximum is. Where I've just sketched it there, it looks like maybe the maximum 6. I would suspect that that is not correct. But let's see what Desmos tells us. So y equals negative bracket 2x plus 1 cubed bracket x minus 3. Okay, so it looks like I got everything right. The only thing that was way off, as you can see, I got my zeros and my x-intercepts, or my y-intercepts correct, but it goes way, 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 way up. And it turns out the maximum is actually 126. So that was off by a bit. But you know what? I still don't consider that to be a bad sketch. One, because I was trying to make it fit on the graph, so I was just using the graph as my boundary. And the other is really, it's not easy to know how high it's going to go. I probably actually, as I was sort of hedging my bets before I sketched it on Desmos, saying that my vertex probably wasn't right. And the thing that gave me sort of a tip-off is the fact that this point and this point are so close together, it must be going up quite steeply. So that means that it needs to go quite far up before it gets to that maximum and then come back down to hit the x-intercept of 3 again. Let's do another sketch. Sketch the polynomial function that has zeros and other points on the graph. Okay, it's a quintic function, degree 5, zeros at 1, 3, 4, a 0 of order 2 at 2, and it has a y-intercept of negative 24. All right, well, we can put that all together and see what we get. I don't have to make an equation out of it. My first instinct is to do that, but let's just see if we can graph it without doing that. So it's got zeros at negative 1, positive 3, positive 4, and also it has one at positive 2, but this one at positive 2 is a degree 2, so we know that it's going to turn back at that one. It has a y-intercept at negative 24, so again, let's just pretend this is negative 24 so I can make it fit on my graph. I've got these 5 points, and I have to make everything fit. So maybe I think, okay, it's going to come up this way and then hit this one, but my next point is this negative 24, which I'd have to get to next, which would mean it would have to either turn back here like this to get through it and then turn around. But I can't do that because that 0 of negative 1 is not an order 2, it's an order 1, so it would have to go through it. So it has to go through it, but if I'm going to get back to this negative 24 again, then it would have to do something like this, which of course it could do, except there would need to be another 0, which we weren't told about, so we can assume that that's not happening either. So what I'm saying here is that it seems that there's no way for me to go through those first 2 points on the left if I come up from quadrant 3. The only way I can make it work, and it'll work quite easily, is if I start in quadrant 2 come down, go through this negative 24, and go down however far it goes. Again, we're not going to worry about that. Now it can come back up and hit 2, and it does have to turn around here because it's order 2, and then it's going to go down a certain ways. I don't know how far. It's going to hit 3 again. This time it's going to pass through, and then it needs to turn around again and pass through this one. So that would get me a sketch that hits all the intercepts and also does the appropriate behavior at the intercept, particularly at the x-intercept of 2. Now, if I back up and take a look at this, this does look like a quintic function. It goes from quadrant 2 to quadrant 4. It's got 1, 2, 3, 4. 1, 2, 3, 4, yeah, 4 turning points. It's got 4 x-intercepts. Those are all things that could work with a quintic function. I would go so far as to say it's quintic, and I could even predict it's got a negative leading coefficient. I seem to be missing part of my next part of my printout here. Luckily, I don't think there's any more examples. Let me just take a look somewhere else. There are some key concepts. I'm just looking on a different computer screen now. There are some key concepts which clearly we can't see at the moment on this video. And then there's homework, which again we can't see in this video, but we don't need that for the video. I'm done the teaching part. The rest of this printout that we can't see, you'll be able to find if you look in your OneNote notes.